All right, so without further ado, let me welcome our speaker, Pak Latif. So yeah, you can continue with the session.
Okay, thank you very much. Okay, so for the subject today, field development plan introduction, we're going to go through the subject. We have to go to the introduction and then set up a competent team, the G&G assessment. So we're talking about the static modeling, dynamic modeling, and then we're talking about how the analysis of data, the development strategy, and so on. So that's more or less the topic we're going to talk about today. Okay. So for introduction, you can see that the field itself, like I mentioned to you, we have to go into cover for FDP, the top from A to Z in terms of the development of the field. So acquisition, as you know, acquisition is talking about hiring a block, for example, or booking a block. For example, in Peninsular Malaysia, there might be a block being offered by Petronas. So the bidding process we go. And then every company will come in and try to put in their strategies and their work scope, as well as try to put in what are the minimum possible expenditure or budget for the field. Once they win the bid, of course, you start to do the exploration campaign. Exploration also will cover in terms of seismic, try to scan the area and try to understand the potential threat within the area. Appraisal, when there is, of course, during exploration, we do one well. Sometimes we call it wildcat. And then the data will be analyzed, linked to the seismic, and try to predict, what are the potential of that area. And then appraisal. Appraisal means that you want to reconfirm in terms of with the better information from one well plus your seismic. You need to do appraisal drilling. And then sometimes it's one appraisal, sometimes it's going to be 3 to 4 appraisal, depends on the size of the field. So with more wells drilled, with more data evaluation, more coring, more well testing during the appraisal stage, the detail of or the accuracy of the data is improved a lot. And then of course at that time you can see the calculation, the integration between seismic and wells, they become much more comfortable. And then sometimes they plan to do another 3D seismic on the selected area where they have the better understand about the field. And then of course the plan we start to talk about, what if we develop this field, what are going to be the potential revenue and the economics of it. So that's the appraisal stage. So once we are ready, we are understanding about the field, then we develop the field. Develop the field, of course, we'll be involved with the construction of the platforms, how many wells to be drilled, what is the strategy for the production, reservoir management, is all will come in. And once we completed the drilling, of course, we're going to produce those wells. Once we produce the wells, of course, production itself have a different challenges because we have to manage the production, from the ground to the surface. And then once from the surface, we have to process it properly. Make sure, if the field have quite a high CO2, we have to remove the CO2. You have to contain high, for example, sulfur content. We have to this lead content. We have to really remove the lead content, and also on. So the contaminants in the oil itself have to be processed. If it's gas, it's going to be a different strategy for development. If it's oil, it's different. So it's going to be, of course, challenging. I think, as you know, they're also now talking about the hydrogen development. So there's not like a gas field, but it's producing hydrogen. So if you read through the literature, you can see that in Philippines have quite a big reserve of hydrogen. So they're thinking about how to develop the field. Rather than producing methane or gas, they're going to produce hydrogen. That's a new era in terms of field development. So once you have finished the production for 15 years to 20 years, even up to 50 years, then you have the well is going to die. There's no more economic production from the well, even from the field. Then you have to abandon each well. When you abandon each well, then you have to talk about at the end of the contract, you are required to remove the facilities. And that's what we call the term decommissioning. Okay, that's more or less the summary. Okay, so what is FDP? FDP, you can see come up with the FDP, Field Development Plan, FDP. And this is document describe the subsurface business plan, and then of course to seek the management approval with all this information about the potential revenue, the economics analysis, the strategy, the potential of the field. Because what happened when you go through the field process, you have to really confirm the original oil in place, original gas in place. That is getting through all the process of seismic. You remember we think about drilling the White well, and then we do appraisal well. All those information linked to the seismic information with all the new technology that we have now with AI and machine learning. The accuracy of the area or the analysis will be much better. So we are going to have a better values or prediction on the oil in place and gas in place. And of course, at the same time, with the data that we drill, the information, direct information from drilling wells, then we can more or less have a better understanding about recovery factor. And of course, we got the economics of it. So of course, in the project, you have to understand the CapEx, capital expenditure, and the OpEx. And of course, there's the two OpEx. When you do the project itself, you have operation OpEx. Then when you produce, there's a consistent OpEx throughout the field life. Of course, the net cash flow, we understand about how much money or profit you are going to get it. As you know, when we talk about the economics, we actually, as operator, we develop the revenue coming from a country. So the country will demand for a better share of the profit. So normally, in average, the total profit will be shared about 20% from the profit. So 80% will be more covered by the government. Of course, at the same time, that will be part of the project cost involved with the 80% share to the host government. Okay, economic study like before, it's all covered in terms of the study. You know that it's going to be quite difficult for the economic because you're talking about so many variables, so many uncertainty. So you have to really judge the economy itself. Most costing will be done based on the basis of P10, P50, P80. So the three levels. So the P10 is based on the best result that you can have. The P50 is more or less an average. You can go something that you go something in the middle, and then you can be more profit. It can be lower profit. But when you go to P80 is something that is we call it very difficult. You're expecting some failures, some problems, some misjudgment. So the P80 numbers will give you a cost for the project. And normally, sometimes management we see that some management like to see what is the potential lowest number if the project does not meet certain specs, certain KPI. So that is where judgment will be done by the management. But so far, you can see that even if P80 numbers, which is the worst number, is still show economics, then the field is going to be in a very good safety health, economic health to be considered, to be executed. So that's how the number will looks like. Okay, then we go to the execution process for this FDP. So execution process, FDP, you can see that we have got a lot of this here. We can see that as we discussed before, we have the looking for the block acquisition, and then we explore the area, then we develop then we develop the information and try, and then we development drilling, as well as we put it on production, and then we put abandonment. So this is the stages of the field life. And of course, like for example, for number one, we're talking about acquisition. A national oil company will be invited for the bidding, and then we find partners to get involved with this investment. And then we invite the partners to be involved with all the discussion. And then, of course, everything will be, assigned to with Petronas for approval and so on. Okay. Then for number two, we start to do the seismic, we start with processing, then we define the trap, do the exploration well, then continue with the appraisal well, and then we try to all processing of linking the data from wells to seismic. And of course, to some of the data that we go in for this during this appraisal drilling, we're going to do extensive logging with high quality logging. We do coring, we do production testing. At the same time, once we have those information, and then we come up with a certain model, aerial development, and then of course we establish the project economics based. This is the preliminary project economics based on what we have, and we try to put options and try to evaluate the risk and so on. So after all the process of evaluation analysis of data, then we have the number three. So we go back to the data itself based on what we written. evaluate the risk, and then we develop FDP to really going to have the project on our radar. Yeah? This is more or less the interesting stage. So this is where the money will come in. A lot of money will be spent in phase number 3. So phase number 4, of course, we introduce the reservoir management plan to understand, how to maximize the production, and then how to really evaluate the potential field. Because even when we are in all this stage 1, 2, and 3, you will realize that this is some of the missing data. The field itself is so complex. Sometimes you have missing, some spot is missing. Sometimes you have missed a few of the potential reservoir reserve. So this is during the development, with all the data that you drill, you have more information, you have more real data from production to see whether some of the estimate of the reserve might change. But in most cases, what I have seen in Malaysia, we always underestimate, Whenever you go and try to develop a field, you will find out that it's more than what you expected. Because what happened when geologists, geophysicists, they try to evaluate, they are worried about mentioning the high number. So they try to be more conservative. But when we actually develop the field, you can see a lot of surprises, a lot of reserve which is not being captured is being there, So of course, some area is not being linked to one other area. So that's where you find out that some reserve being captured only based on the understanding about the area. Actually, what happened, there's a lot of area which is linked to the reservoir, or some area not being captured because of the structure is not very clear. Then you have all these surprises of extra revenue or extra reserve in the field. So that is normally happening in Malaysia lah. So for example, like we have the SO well, the Tapis, the Pulai, we expected them to last only 25 years, but even they are approaching up to the 40 to 50 years. So that's the different the advantages of taking the risk, understanding the field, give us the advantage. Okay. Then number 5 is field decommissioning. Actually, we want everything is no more economics. The production is too low. So when your for example, your operating cost to run the platform and the facilities, the project is, for example, it's about $100 per day, and then your production is only $80,000 a day. So you're going to go, you're actually at loss. So that's why you start to really request, ask for the field decommissioning, remove the platform, and then giving back the block to the host government. Okay, interesting. It's so much detail, but this is on a high level. So we go to deep dive a bit as per we go on. Okay, first of all, the field assessment, I think we more or less have gone through the summary. We try to understand the opportunity of the field. Then this is a green field. We see whether what we can do, justify FDP by feasibility study. We do feasibility study initially. For example, once you drill one exploration well, then you start to make some judgment. Say, for example, before you go for appraisal drilling, you have to spend about one well is about 60 million, 50 to 60 million for the appraisal well. So you want to drill 2 wells, it will be 100 million. So before doing that, sometimes you do some feasibility study to understand about the potential before you start with your appraisal. So once you have the appraisal done, then we try to do some economics, try to see what if, it's a different scenario. What if I have a big reserve? What if I have small reserve? And so on. Then once you have the scenario, then you find out what is the missing link. What are the information that you need to improve to be able to help you to accurately estimate your economics. So this is where the appraisal drilling will come in. Appraisal drilling will come up with all the additional data, like coring, like well testing. That is where you have more information, more confidence on how we should proceed with the project. Okay. And then the same thing, of course, for project execution, there is a process flow. For field assessment, okay, like I think we discussed just now about economic viability. Once you decide on the economic, then you plan for your FDP. Of course, this is only the planning stage. It's not the execution stage yet. So the initial FDP, we set up a project team, appoint the team leader, the project manager, and then we start to really see the data. and then the data, because the data itself will help the team to really interpret the information about the reserve, because we always worry about the reserve and the recovery factor. So once we have the information available, then we're going to do a hydrocarbon model, and then which is required to go to have more data. Then we're going to have that. Normally there will be a process of doing some lab analysis, petrophysics data analysis, and so on. So PVT analysis and so on to really improve your reservoir understanding. So once it's acceptable, and then of course, if not accessible, you go and recycle again information, get more information, try to think about how much you have to spend before you decide to go for the project execution. So once you say that uncertainty is also acceptable, you can proceed. So when you proceed, you have to prepare a reservoir modeling, then you develop the best option in terms of how to really develop the field, in terms of understanding about the reserve itself. And then with the economics options, we have put a database to see whether it's acceptable or not. Then once acceptable in the process of economics, then we're going to implement the project. So you can see that, all this information here, we involve drilling plan and then depletion plan, because it's not going to be that simple. This is going to be like, for example, you have a reservoir, you're going to produce from the reservoir, and the reservoir will be depleted, and then after some time, the water conning will come in. So you're going to produce water, and then you have to start to have less production, and your facility is aging, your wells is aging. All those information have to be processed to understand what are the integrity of the area of the field as well as the well. Okay, so once we implement the project, of course, it's going to cover a few more work scope, the logistic, EIA study before you implement project. So EIA is environmental impact assessment. So this environmental impact assessment is more towards before you do a project. This is the standard, international standard, that we have to do the environmental impact assessment. And for the new area, normally they will ask us to go with the full EIA study. When you are in the early stage of exploration, because only one well and only a short-term duration, you can do a desktop EIA. But for the project, such a big project, you have to do the full EIA, covering all the potential sampling of the area, getting the benchmark, and then giving all the strategies of how you're going to manage pollution. Then you can given the approval by the government to proceed with the project. Okay. So you have any question, just put in your chat box. Then I will try to answer most of the question, inshallah. So just even you can interrupt me if you have any question. Open up your speaker. Then we to discuss immediately, because it's quite interesting subject, and I know everybody is a bit is a bit excited, talking about what is meant by this and that, and then how you manage certain information, and then what happen if you don't have information, and then if you want to get information, it always be about cost. But if you know that in oil and gas, getting information is not going to be very cheap. For example, you want to do seismic itself. To do seismic is cheaper, but you need to do that earlier because you want to spend less money. But the moment you have that confidence, you can justify to spending more with the 3D seismic. Okay. Then somebody asked, what is 4D seismic? That's that we talk about later lah. So we're talking about in this case only 2D and 3D seismic. Okay, just put in your question or your whatever even your comment, if possible, in the chat box, so we can discuss in this forum lah. Thank you. Okay, we proceed. So FDP process, in terms of the summary, we still talk about the same thing below, the field data that we're going to have, and for the FDP, then we start to do the static modeling, the dynamic modeling, and then we start to create a development option for the field, and then we start to design the field engineering, and I think this is front end engineering and design. So FDP. So you can see that from each section here, there will be a lot of information. Like for example, for static modeling, we need to have develop a structure map, and then from structure map itself, we can see a different version. Nowadays, with the computer assisted, we can even have a 3D version. We can rotate the model up and down, and you can have different colors, to see that this color representing most likely oil, the color is representing potential gas, and then this is highly potential gas, highly potential oil. So it's all different color. They help the audience to understand the potential. And of course, that is only on prediction. Never think that whatever being shown to you is all accurate. It's all still considered like prognosis, and the accuracy is still within a certain range, like 60% accurate, 70% accurate. So you don't take it for granted once you see a number, But this is talking about geological data. No something solid is coming in or positive. It's everything coming from analysis, coming from prediction, expectation, and so on. So once you have the map here, another important subject is called depositional environment. That means that certain area, you have quite a good study being done before, talking about is it the area that is coming from the coastal area, or is it coming from the alluvial area, which the deltaic area is coming from the ground, is coming from the inland, or coming from the deep water side, depositional, is it coming from the formation of the carbonate in the sea, because we have the batu karang, they call it. So that's all historical will help us to understand about the nature of the quality of the reservoir of the field. Same correlation will be done with the rock. So we try to correlate from one well to another, and even we have some offset wells from the nearby field, we try to see the pattern, and of course that will help to understand. But as I mentioned to you, we have exploration well, we have reservoir well. We're going to link those information of wells to the seismic. And with the current technology, with AI and machine learning, we are going to have a better correlation and a consistent result. Because as you know, when we talk about analysis of the seismic, it varies from one geophysicist and geologist to one another. So you have the one team coming in, they will develop, they will try to interpret the data with their knowledge. But you have another team coming in, you're going to be a different data, different answer. So it's very, we call it very subjective, and it needs expertise and experience and good judgment. Good judgment. Okay, once we have that, during static modeling, they are going to develop the porosity map. So porosity map will be coming up from some study from the core. They're going to send it to the lab. So the fluidity analysis, we do the study on the porosity, the saturation, the flow context. We also done through the seismic analysis. So finally, you have the net to gross map, where you're talking about what are the possible spaces available in the rock itself for the hydrocarbon to be there, And then finally, they will come up with the oil in place. This ST is stock tank originally in place, oil. And then gas originally interpreted in place, GIP. So it's a different kind of term. Sometimes we just call GIP, GIP. So gas in place and oil in place. That's normally the understanding. Also, once you have done the static modeling, we're going to go for dynamic modeling. You have the flow assurance to check whether the flow within the rock is there, the permeability, and so on. Drive mechanism, you can see that, based on the area, based on your seismic interpretation, you might see some of the water level coming in, and then you try to predict how big is that water available for the push. So once you have the power from the water, the volume of water is huge. That means you can talk about natural flow from the well coming from the powerful reservoir. So you can see all this information will be gathered, predicted, and forecasted by the reservoir engineer, by the geologist, and then of course we come at the productivity index. Productivity index more towards like any pressure drop, how much is your barrel being produced, or how much gas being produced? That is the productivity index. Depletion strategy is always like, for example, it's a big field, you want to produce from 110 wells. So you can see that some of the wells, because of the structure of the reservoir and anticline or fault, so you can see that some of the well will produce more and causing the water to go up earlier. So maybe you want to avoid the water to come up earlier to one side. So you will try to maximize your production by controlling the depletion, so that all the well will be producing oil or gas without water encroachment, and then you have the best volume to be calculated. Otherwise, one of the well will be more being killed by the water that is coming in earlier, because of the failure to follow the depletion strategy. So sand phase completion, normally talking about the sand phase is talking about, we have the casing, we have got preparation, then talking about the well bore radius that is going to be affected by the skin. We're talking about how the production coming from long distance, going through the field. Imagine we have one well, we have the oil coming up from the 1 kilometer radius, for example. It's all coming up with all the dirt, with all the fines, and then it will cause plugging later on. So what's going to be your solution to solve the issue? And of course, if after some time you're going to plan, for example, maybe after 5 years, the pressure in the reservoir start to depleted or down. So we have to think about how to lift the oil coming up to surface. In Peninsular Malaysia, normally we discover our oil reserve, our oil reservoir at shallow depth, maybe just slightly over our formation pressure. So when you produce the well for about 6 months, then there's no pouring naturally anymore. So most wells in our area in Malaysia, we are using artificial lift. They call it gas lift system. We run immediately together with the completion, understanding that within 6 months you're going to have the production down. It cannot flow by itself. So with gas lift, then you have continue production of the area, even though it's depleted. So gas lift have been popular because the effectiveness of producing the well even at the lower pressure, depleted pressure. Okay. Production forecast, of course, will be done during dynamic to see how the production will be, better up to maximum, and then we try to decline. So there will be a decline pressure, a decline rate for each reservoir or each well. And then, of course, EUR is the estimate or ultimate recovery. So you're talking about the reserve. What will happen to the reserve, we're going to monitor. For example, in your early calculation saying that, that well, one well A should be producing about, let's say, 800,000 barrels, for example. Then you try to monitor to make sure that, during the field life, during the year 0 to year 20 or 25, that you're going to recover as much as possible of the reserve within the well itself. At the same time, of course, you're going to link to the total field to see whether if the total field have a reserve of the 200 million barrel, are you going to have that recovery of 200 million barrel based on your forecast and your observation, your monitoring, and so on. So it's part of the reservoir management later on. So when you do the development option, you're going to apply whatever you plan for the dynamic modeling. You're going to compare. This is where you call it digital twin will come in. So you have one twin being designed for the dynamic model, and then when they develop the field, you're going to see the comparison. So you have a queue. Let's say you have 20 items for the twin, and then you're going to compare and see the result. Some of the area you are almost like on par, some area you are a bit down, some area you exceed the requirement or the KPI. So that's during the development stage. So all this process is actually being done professionally. We put all effort, we put all the strategy that we manage the field to the optimum production and recovery. Okay. Some you have that, then of course we go for this is front end engineering, talking about really going for the construction of platform and so on. This is purely on the mechanical side, where we talk about building the platform, and then of course sometimes we understand what going to be the collection of the drilling cost data, and then of course the economic study will be done during the FEED as well, because they are going to follow the development option. We will outline what are the type of development option in terms of how many platform is it going to be, what's the pipeline requirement, is it going to be like a one water pipeline, one gas pipeline, one oil pipeline, and so on. So all those kind of strategy will be more or less supported by front end, and the data will be based on the development option. Okay. Any question? This is quite a lot of information. Even in one page, you can see there's so many items to be discussed. And of course, for me, it's important for you to understand the topics. So you have the opportunity to go to your ChatGPT, then you can start to explore on each subject, Like when you go to ChatGPT, you ask, please explain to me what is top structure map. He will give you maybe about 2 pages or 3 pages of information. Then you ask about the flow assurance, then you start to have the knowledge of each item. So now I think we have the opportunity to have the, some our technical advisor, the ChatGPT or DeepSeek or so many things lah. So even I think from the co-pilot, it can give some help as well. Huh? Okay, question. Then you just put in your chat box. Then we see what we can. Let me say. There's no question yet. Anyhow, put your question. I think it's quite complex and there's so much information, high level. So I think when we go through the detail, you start to realize that you need some clarification or some information about that particular subject. Okay. So analysis of field data, this is the beginning. So when we have the data available from JNG, then we want to understand what are the kind of analysis that we should do. So database quality, this is important. For example, when you do seismic survey, you must understand that what when the seismic survey is a company. The company should have the experience to have the latest technology into doing the seismic. So of course, every time that it's going to be high quality, it's going to be very expensive. So not this is a challenge. So normally what we do actually, it depends on our requirements. Maybe because of like I mentioned to you, even though you have a good seismic, but you don't have a good geophysicist or geologist, then you still have the same problem. So in other words, it's all subject to the combination. Of course, we try to have the best. So the best company to perform the seismic and the best team to evaluate the results. Okay. So number two, the seismic interpretation is gone through a few process. Sometimes it's being done by different companies. So seismic is done by company A, and seismic interpretation sometimes is done by company B. Because normally this seismic interpretation involves quite a huge computing power. Sometimes it involves a lot of this, programming and so on. So that's why, we have to look for the best seismic interpreter to have the best results. So you can see the difference. So seismic can be done by a different company. Interpretation will be done by a different company. As you know, nowadays we have artificial intelligence and machine learning to do that. So some company we have to spend some extra money. If it's so big company, or for example, when we have the big reserve, potential big reserve, it's always interesting to do another processing through the AI and machine learning. Okay, special studies, normally we go to, depends on the processing. Sometimes we reprocess the seismic to get more information about the seismic attributes. And then of course, in terms of the quality, accuracy. Just for your information, seismic have some setback. For example, seismic, is going to be based on sound wave. So if there's any huge gas clouds or gas accumulation, gas channel or chimney coming up from the reservoir below, or from the earth below, those gas clouds or gas chimney disturb your seismic accuracy. So this is where sometimes you lose your judgment or your interpretation in that area, then even you can't link between the left and right because of the disturbance of the area. Then you always have the difficulties. Some company they try to drill a well through that clouds so that they can have a better understanding about the seismic result and try to link that to the seismic interpretation that they have, to improve the overall. Because normally that's the area where we lose the prediction on the good reserve. Okay. And then, of course, the uncertainty and mitigation plan, reservoir container size, shape, and so on, reservoir stratigraphic channeling. Because sometimes the reservoir that we have, sometimes if it's simple reservoir like anticline, it's easier. If it's like or between the stratigraphic trap, it's much easier. But in most cases where we're talking about the deltic environment or the near shore environment, we always have all those combination of good sand, bad sand, some shale, some clay coming in. Even in some area, we have some river pattern. So most of the sand is being accumulated around the river channel. It's beside it. Then you can see that to trace those information through seismic is not that easy. So this kind of different stratigraphic trap, different reservoir pattern, reservoir shape will get involved with all the uncertainty lah. Okay. So this is example of the seismic interpretation. The first round, this is fresh. So what they do, they have the seismic interpretation, and then of course, geologists, geophysicists, mostly this is the job of the geophysicists. They try to predict what are the possible layers from the seismic survey. And then they try to see what are the potentials, we call it fault. This is the fault being assigned because they can see the changes here. And the UPG, we see that this is a potential fault. There's some movement of the earth, so there's some fault. What is the importance of fault? The fault is important because the fault actually will create a trap for the gas or oil. So that's why by identifying the right fault system, will give you a chance that you can look for potential trap of oil. For example, this is a potential trap. This is more or less we call it unconformity, a change of formation. For example, this is the 300 million years. The top is 100 million years. So you have a different demarcation of the zone. So this is called unconformity lah. So the GPGs we decide this is the conformity, then another layer, and that may be I think in terms of aging is not done yet. So the aging of the platform will be done once you drill a well. Then you know that each formation here will have certain description, and they try to correlate that to the offset wells or even to the sample that they take. They send it to that to understand about the age of each one. So there's a few study to be done. Of course, when you have the seismic to confirm the accuracy of this seismic, you have to drill a well. You can see some drill well on the other side and so on to really confirm all the information as well as the potential hydrocarbon. So that's important for that. When we drill a well, for example, this well is going deep, very deep. So this well will become a good reference by having all the correlation of all the well drilled with the formation data and so on. If appraisal, we can take core sample, so formation will be taking up to surface, and we do the analysis of the porosity, the permeability, and then the strength of the rock and so on. So this well will help. And like I mentioned, with the AI and machine learning, we're going to link or relate all the information of this well to the seismic. So the seismic will become much more clearer. And we know that this is going to be like, Cambrian, Premium, so all those kind of aging will be done. And then the quality of the formation, is it going to be like sand, shale, coal, dolomite, and so on. It all be understand. We can relate all the information to the seismic. So we can see that, we can, even anywhere you drill in your development well, you start to understand that this area will cover dolomite, discover, for example, coal and so on. This is the seismic interpretation. Okay, so the data, once you have the geophysical data, then geologists become in. So for geologists, you can see that we are talking about the database that we have around this offset well and so on. So we're going to find out in terms of the environment, the positional environment, the migration. So geologists have that skill. They can see from the seismic that is going to be where is the potential source rock of the area, and what is the potential of migration, where the fault will be helping the geologists to understand migration might be happening, might be 100 or 200 million years ago. And then once we have that migration, they will be looking for the trap. So the hydrocarbon will go and migrate upwards. And then if we find a trap, they will be more or less stay there for millions of years before we drill and discover that field. Okay, so they have to understand the tectonic history, because you can see that the earth, if we go back to the study of all the rocks, in the region, even in the area, in the world, there always be some study about tectonic. They understand that what happened to certain area, how the Mount Everest being developed, how Mount Kinabalu have been developed, been pushed up. So all this history of tectonic be more recorded based on the original study, database of the area. Then we go stratigraphic delimitation. As you know that once you have the seismic, there's nothing you can see much. But once you drill well, you start to relate all this into stratigraphic. We have the facies analysis, talking about what are the plankton and whatever there. And then we have the quality of the reservoir and so on. So at the same time, if we have the opportunity to study, there will be a lot of geomechanics study to do, understanding about the stresses between the wellbore. Geopressure, you got pressure, we call it the formation pressure of the area of each layer. So sometimes you have a normal pressure throughout to, let's say, to 3,000 meter, but sometimes you still have a normal pressure of 2,000 meter. Then you have start to have the increase beyond 2,000 meter. So all this information will be captured during the geological analysis. And then we start doing the static modeling. Okay, with all the estimate on the stock tank oil in place, whatever. Okay. So this is one example to show you in terms of the seismic, when do the interpretation, the geologists will come in, they will combine together, will have this cross-section plot. And that is where they tune all those faults. Actually, this is the indication of the migration of hydrocarbon. And they have the layers, and the layer they have some seal cap rock. The cap rock is actually sealing any more migration of hydrocarbon to top. Some cap rock are being leaked, being broken up by the fault. So in other words, if you have any hydrocarbon, it will go to the bite. It can still escape through the cap rock because of the fracture by the fault. So finally going up, and then you might be find any trap. If there's no trap, then you will go to the atmosphere. Then you don't see any more oil of that area. But normally we found out there will be some trap over here that we are able to see the amount of reserve being trapped, and we produce that as per our development plan. So, as I mentioned to you, we're talking about all the study about the source rock, about the migration, and then of course the trap. So it's quite interesting. It's going to be a different topic. If you become a geologist, you see that it's very challenging to really understand all the migration process. The depositional means that is the quality of sand that you're going to trap your hydrocarbon. High porosity, low porosity, high permeability, low permeability, and so on. Okay. And then, of course, some of the area, is so heavily fractured because tectonic movement is a lot. So you can see that in this area, you're very worried that you might not have any trap because any oil coming up from the source rock, you go up and then try to escape to the atmosphere. So that's why, if there's too much tectonic, you're worried that you might have less chances of having a trap. But I think in the world, as we go by, we see that even though there's so much fractured, so much fault, but still there's still some potential of having some small volume to be considered as marginal field, that kind. Okay, let me check chat. Okay, I think chat not much. Let me see just to check the chat. I see. Provide AI generated. That's the one company generated. Or you will probably see. Yes, I think we have some link. If you want to see the link, or there's a link given by Encik Razak. Okay. Okay, we continue. So for field GNG assessment, this is another interesting subject because this is all skill. So we call it an art of interpretation. It's not physical, it's an art itself. And how the skill of interpretation, looking at the graphics, looking at the numbers, looking at the pictures, to give you some understanding about how it looks like. Okay. You just imagine with the new technology of our supercomputing process that even we can do a very detailed seismic, 3D seismic in terms of the geology and geophysics. So you see that it's coming from the seismic, and then you have seismic also have the 2D, and then of course we have the cross section. So you have the XY and YZ, so they can have the 3D seismic, 3D figures for your seismic, and the geologists start to put in all the layers and start to show what are the conformity, what are different age, and then start to show different colors for sand, different colors for carbonate, So you can see such a features. But of course, as a normal, we're not geologists, we are not geophysicists, so it looks like nice, very nice, But how to interpret the colors is all the expertise of the geologist. For example, the color here means that this is the top of the hydrocarbon, not the oil, for example. And then you have some layers here, which is going to be another seal. And then there's no indication of hydrocarbon trap here. This is something unknown or missing interpretation. You just put a blue there. And this is all the fault system, the fault, everything they block. So okay, some layers here, maybe some possible trap, or maybe there's some oil, and below is water. So then sometimes when we see blue here, at that time, this become possible water level, water column, water reserve, supporting the reserve. So all this actually being defined with different grid. So one block here is one grid. So one grid here is by itself have the volume, porosity, permeability, whatever, and then of course the compressibility. So each one have its own. So every layer has its own data. So in this block here, you might have about 2 million cells, for example, and each cell contains its own information. And when we do simulation we analyze interaction between cells. Sometimes, before, normally for this, when we go to reservoir simulation, processing the data to get the result of one well here, for example, it must take about 2 weeks to do the reprocessing. But nowadays, with the fast computing process, most data can be done within half an hour or even 10 minutes nowadays. But still, it's time. So you have 100 wells to process, going to be take too much time processing because it's too many information, it's too minute. But of course, some of the scaling here can be increased or can be reduced based on the requirement. Of course, you're going to lose, you need processing time to do that. Okay. This is approach probabilistic study. So this, of course, when you do all the analysis of the reserve, you're talking about probabilistic, deterministic, to show to Petronas, understanding about how you predict, how actually the ranges of uncertainty involved. Upside potential, of course, whenever we do the assessment here, we try to go to the base understanding about the potential of accuracy, but at the same time, we want to explain potential upside. Upside means it can be more. So of course you separate that as a separate subject. So when you present to the government, or to your shareholders, you're going to show that okay, this is what we believe the volume of hydrocarbon that we can produce, but we might also have a potential of having more. So that's kind of information. Of course, the judgment will be asked by the management saying that how confident you are that you have the extra reserve. Of course, you might say that it's still 50-50, because nothing being done except once you drill a well, that one well, then from that one well, you have production, you have more information about the formation, then you can improve your result. But it's only at the later stage. So that's how the discussion we go around. Okay. For reservoir engineering, you can see that reservoir engineering is another discipline that try to go into detail, understanding about how the reservoir will be more managing the behavior of the reservoir. So some reservoir is complex, some reservoir is quite easy to manage. And then, of course, you have to understand the detail of each reservoir, the porosity, permeability, and in terms of the characteristic of the sizes of the sand. And then is it going to be a compressibility is very important, because I think currently we realize that compressibility contribute a lot to the additional recovery, because compressibility means that the formation itself like a sponge. It can after it been depleted, it start to squeeze down and produce more hydrocarbon compared to what we predicted before. Depletion mechanism is always the same. We have to understand that if we produce from 10 wells or 20 wells from the reservoir, that reservoir will be depleted, and how much is going to be supported. If there's not enough power or energy from the reservoir, then it's not going to flow naturally. We have to put in something to do to improve, like a gas lift valve, water, injecting water, to pressurize the reservoir to be able to produce continuously, naturally lah. But like I mentioned, in Malaysia, we have the opportunity to use gas lift valve, even though it's there's no water drive, but still the well can flow because of the ability to inject gas to lighten up the hydrostatic column and produce the gas as normal. Okay. When you have all this model, it might be completed by drilling a well. So when you do the well construction, the well construction should be able to manage all the reservoir modeling requirement, the depletion requirement. So for example, you want to run the 3.5-inch tubing for your production stream, and you say no, because of the depletion. Maybe we need to think about having the 4.5-inch tubing, for example. That all this discussion is related from one discipline to another. Okay. Then reservoir engineering, we cover also this is a very important thing, like reservoir management plan. They call it RMP. So reservoir management is that they're looking from the day one when they start to produce to understand about what is the volume being produced, what is the pressure behavior, what is going to be any temperature changes that can happen, and then they try to understand, what relationship between one well to another. Because it's like a plumbing system. For example, you have a reservoir, you have all your piping coming from all, then you open up the tap. Sometimes tap will open up this area, tap is open up bigger, this area is small. But you try to understand that you should be able to produce as much as possible and try to avoid water coming up too early, so that you can maximize the production rate. Of course, when we do the reservoir management plan, they understand when the water will coming in, when the gas start to really taking over the production, so having less oil, more gas, And then water sometimes once you come in, then the water coming up too early. So you have 80% water, you have 10% oil, and then 10% gas. That will come up to the stage. So all that will be studied with the simulation. The reservoir engineer will compute based on the recent data. They have the data, they updated information, they predict the future. So this is where they can understand what will happen to the water coming up. For example, if the water coming up is too big, they have to think about installing the water removal processing on board itself, because when the water is coming in, they have to remove the water and have the clean oil going through the export line. But at the same time, the water must process because it have some contamination. They have to process, clean up the water before this disposal to the sea. So all these facilities have to be think about and put in phases. So sometimes you need this water processing system. Sometimes you want to inject water. It's all being planned as per the reservoir management that can tell us when the water is coming out, when the gas is coming out, and so on. Okay. Uncertainty management is always be there because we know that this project, whatever we're talking about oil and gas, we're talking about so many uncertainties, so many variables involved. And then everything that we have in all prediction, we do everything on simulation, we predict, and then based on the data. So of course some of the prediction might be going off a bit by 5% or 10%. Then of course you see the impact. Some is manageable, some is not. So one is not manageable, of course you have to do something to do the remedial and then try to do the corrective action. So in terms of the recovery for the RSP, I think reservoir static something lah. I can't remember. This is reservoir plan monitoring plan. Also the same thing. Whenever we produce the production history of each well is always important. That everyone we produce, we're going to monitor the production history of each well, and we relate with our simulator to see whether it reflects the simulator behavior or there's something that is actually changing that cause the result to be different. It could be better, it could be worse. It depends on the result, and we have to rerun the simulator to match the result itself. So as we go and produce, we have more information, more of the data that reduce the uncertainty that we have go along. So we always think about optimization of the production. So in general, number 7 recovery factor is just a guideline, because the oil recovery factor depends on number of wells. For example, you have one field. If you have 3 wells in the field, of course, the recovery factor will be very low. But you more, well, let's say you have 6 wells in that field, of course, you're going to be very higher recovery factor. But what happened actually, the more wells we drill, the more expensive will be the project cost. So we try to come up to the break-even line where the cost of the well is willing to make is just enough to have a good economics for the recovery, because of course you can put 100 wells in one field, but the cost of the well is going to be very high. The project cost will be exploded. So you might think about maybe 20 wells is enough rather than 100, but still covering enough reserve and then to produce. And of course, as we go along, we're going to optimize the field, understanding about the potential. Then we can think about adding more wells later on. Okay. So we have about 2 minutes before. Let's try to finish this. And of course, as I discussed with you, when you develop a field, if this is onshore, for example, you start to drill a well and try to produce from the reservoir with individual wells. Because for onshore wells, we can have vertical well selective. So a vertical well is easier to drill. And then in terms of the friction to flow the product to the well is also very low. So it's always the best part to produce the well vertically. But for offshore, you might have one drilling center here. Then you have one well going to the reservoir, and then you have a directional well going from the same drilling center to this target here, and then another well going through another center, to another target here. So offshore, because it's very expensive to construct so many structures, so we're talking about one main structure and we did multiple wells. So from this structure for offshore, we're going to drill another well here, another well here, and here. So that's the strategy to reduce the cost. Okay, this is another sample of how the planning of reservoirs. So it is a big reserve. You can see that they try to see that, okay, for example, we can have, let's say, 100 wells in this field, but based on the economics calculation, they must say the best spot, the hot spot is just to have about 30 wells. So they have only about 30 wells. But initially in the process, they try to maximize everything. Of course, the economic, we try to screen back, whatever is going to be the right decision or not. Because like I mentioned, if 100 wells being planned, but it depends on the economy, you say that no, we have to go for the hotspot, the highest productive well, then we might be collecting only about 10 or 20 wells only for the field. So that's how it looks like. Okay, I think we stop for a while and then we continue with the static modeling later on. So we have a short break, 5 minutes, then we continue. So 11:05, we start again. Thank you very much. See you later. Okay, Assalamualaikum. Then we come back again. So let me check my volume. So if you have any issue with the sound system, it's too slow, maybe too quiet, whatever. If you need volume to be increased, then just put it in the chat box. Then we try to to do the judgment, the adjustment. Okay, so static modeling, as you know, is going to be a second stage. So we have more to go, But anyhow, I have to speed up a bit. It's quite interesting subject. So static modeling is actually we're talking about the construct of the structural maps. The geologists will try to develop a good understanding about the field, the depositional environment, and then of course giving some the data on the formation with all the seismic and the well drill. And then the correct mapping techniques have to be done to make sure they have the better accuracy among well to well. But the challenges is always that for example, if you have let's say a field. So you have the formation of rocks. When in the original formation of rocks or the reservoir itself, there's so much of the differences. Like for example, some area they have a very good sand, some area they have very bad sand. So you drill one well and then you just hit the good sand. It doesn't mean that everything will be good sand. So that's why it's always be understand about the seismic itself, and then about the deposition environment to understand that whatever you have might not be matching to all everything together. So when they did a well, they try to see the chances of consistency. For example, from one well to one other, they try to correlate to see whether that sand is extending continuously to the other side, or for example, they have a good sand on one well, but the bad sand on another well, so they have to predict what is expected in the middle. So there's a lot of uncertainty, a lot of adjustment, a lot of ranges being used in the analysis of this structural map. Okay, so fault system must be also be there. Some, like I mentioned to you, you have one team coming in, they put it at 20 fault system, and then we have another team coming in, it can be about 40 fault system. So it's all big judgment, it's all been based on the experience and the understanding about the features from the suspect. But because I mentioned to you with the technology of AI and machine learning, we have the consistent knowledge. We gather all the knowledge with machine learning. We understand about the consistency, the result. Then the machine learning will help the AI to interpret all the fault that is coming in. So that's a big help for us with the new technology coming in now. Okay. So for structural modeling, you can see that we have all the stages of 1 and 2 and 3 based on our information or data collection, and talking about the static modeling, geometric modeling, and so on. So based on this particular area, so the first one, phase 1, we're talking about acquisition 3D again. So we're going to analyze all the data that coming up from 2D, 3D. And then of course we have the mapping system, the marker. The marker is quite interesting because some of the software, they can do a very good marking 3D system. It's very clear and very easy to interpret. Of course, at the same time, static modeling, we do the depositional environment, tectonic model, and then they establish the reservoir marker to help or this is the static model over here. So the yellow is a static model. So the job of static model is linked to all the rest of the dynamic model. This is the static model, the yellow color. So when we construct the static model, we go to the next step. This is the dynamic model. The next step, actually, we cover the dynamic modeling. Is where the flow insurance will be coming in, and we have the drive system. Drive system, is it water drive? Is it a gas cap drive? A drainage point, how many wells we're going to plug into, punch into each reservoir. The index is going to be the production index per pressure drop down. For example, in the reservoir, when you have the 1 psi drop, we are going to produce 20,000 barrels, for example. Is it the 2 psi drop, it will be about 40,000 barrels being produced. So that kind of index, we call it, is per PSI drop, pound per square inch, the pressure drop lah. Depletion strategy, like we discussed before, sand facing, about the damage around the wellbore radius effect and so on. It's all done during the sand facing completion. Artificial lift, if requirement. In case of like the depleted reservoir, sometimes you will discover oil in a very high pressure area, then it can be naturally flow for at least for 10 years. Yeah? But sometimes in our area, in Peninsular Malaysia, we have oil reserve slightly overpressure, not too high. So we need to have the gas lift to really continue producing that well. Forecast is based on the reserve, based on porosity, based on whatever, how many wells we have and so on. Then we try to predict the reserve that we're going to recover. So the reserve, like I mentioned to you, is going to be like, for example, you have 100 million barrels in the reservoir, but you have 30% recovery factor, you're only going to produce 30 million only, because the rest will be still trapped between the rocks and still far away, you know. Like I mentioned, if you have more wells, then the recovery factor will increase. But more wells mean more cost. So we have to go and find out the break even, the fine line, to be more economical, less cost on well, but still have a good reserve for your development. So that's a strategy, because the cost of the development is very expensive. If you go onshore, then you're talking about, if you go to see some of the drawings I think in Sumatra and South Sumatra, chevron drill, even every 100 meter, they will have one well. So it's so much well of course, onshore is different. Okay. Then of course, the dynamic modeling, we go through the process of the yellow. Normally, the modeling define the producing condition, both surface and subsurface. You can see that what are the dynamic modeling here is also contribute to the requirement, like casing design, turbine design, and so on. So that's the dynamic modeling. It's showing about the flow, the COVID. You remember the process here is huge itself. It's not just one title. Even though you can see it's only one, but it consists of a lot of assignment and work scope to be done. Okay. So development strategy. So once we find out that the reserve is there, we're going to see how we're going to develop the field. So development option, for example, this is for example of subsea completion. You have a PSO at top, and then you have all your drilling wells. So your template here, we drill. This is seabed, either seabed or subsea facilities. We to drill one well here, tapping to one reservoir here, maybe it's 1 million barrel or 100,000 barrel here to be produced, recovered. This is maybe 500,000 barrel. Maybe this is another 800,000 or 1 million barrel. That's all this spot to recover based on the trap. So this one trap here, independently. Then all this well, and all this oil will be produced up to here, and then they will link to the manifold, and then going back to the facilities where it's going to be processed. So here he might have a processing facilities where all the crude with all the gas, the contaminants, and all the CO2 and so on will be processed, and then there'll be a storage somewhere. So they will have a storage, so facilities for processing plus the storage. So you can see once they fill up the tank, maybe this is a 1 million barrel, 1 million capacity of storage. So if the field producing 20,000 per day, then it's about 50 days to mark up the 100 million barrels. So tanker will come in, the starter tanker will come in to load the crude, so it's continue producing. So something like that. So this is more or less the model. Either you go for subsea, you want to have set a platform. It's all based on the strategy. For example, if it is very deep, of course you cannot have the platform because it's going to be very big platform, so much steel. So you're going to cost you a lot. So with this, you have something that is mobile, that is going to be, after some time, for example, after 20 years, you can still use this, you can still sell this FPSO to another operator because, you already use it for 20 years, for example. And then, of course, the condition must be always maintained. So this is strategy. It's either be subsea, it can be platform, it can be, for example, they have a separate addition pipelines. For example, from here, other than going to the FPSO, maybe it's also possible that you go and share with another platform, So you link to another platform, nearby platform. So you share the facilities, you spend less money. Rather than FPSO, you are going to share with another platform. So that option is available, especially when the field is have the nearby neighbor is producing, and they can have the extra alish, they call it extra facility, extra volume for you to tie in. Then it's much more cheaper to do that. So in Malaysia, we have Petronas that is controlling the total structure. And even when you presented to them, they will try to, to question you about, can you tie into the another field? Because they know the information about the nearby field have certain capacity. For example, they design the field to handle 100,000 barrel per day. But after 5 years, the production dropped to, let's say, 60,000. So they have about 40,000 extra. So if the field have the production of 30,000, then it can tie into the platform, and Petronas will help to get the buy-in or agreement from another operator to allow you to come in lah, at a special rate to be charged, or OPEX or tariff, we call it. Okay, this is model, the development model. This is another one model where you're talking about, let's say marginal field. This is actually we call it MOPU, where you have the facilities on the board. It's a like jack-up rig for shallow water, and they can use for drilling. At the same time, they can be used for the storage itself. And then once you have the production coming in, of course, this initially when we drill this well, it can drill multiple. It can drill 6 wells, it can drill 10 wells, and so on. But once you have that production, we have a storage system here for a while, and then they pump the oil to the FPSO. Sometimes the well has been designed whenever coming up from the ground, the oil will going straight away to the tanker. Sometimes they have some temporary transit storage. It depends on how they design the capacity here. Because this MOPU, mobile offshore platform unit, is actually quite small. So you just imagine that they are not able to handle so much equipment facilities. So it only on the certain kind of manifold, certain or to burn some extra gas or to handle some contingency. The rest is actually going directly to the FPSO, where they have the processing here plus the storage. If the platform is big, then they can install the processing facilities here. So this is purely become a storage. So for example, it's 700,000 barrel storage. So if the field is producing 10,000, there's about 70 days. We call it the time, the transit time before the vessel come in. So this is the tanker they coming in and out to load the oil here. So just imagine if you have a small volume of, for example, the 500,000 or 300,000 barrel, you're producing 10,000 barrel, then it will be about 30 days. Then you have to really have the tanker come in every 10 days. You coming in and load. So that's why all management of this tanker is done by Petronas marketing department to make sure that because all these facilities belong to Petronas. Operator is only manage the operation, manage the FPSO, but the rest of all the revenue actually be handled by Petronas, and they will more or less do the marketing and the selling. Okay. So another one is that you have the nearby platform that I mentioned to you. We can share, so we don't need to have the PSO anymore, because we just go straight to another platform. The platform here might have normally you can have a special pipeline, so it can handle big volume. For example, you have a capacity of a production like 100,000 barrel from multiple wells, from multiple platform. 100,000 barrel. If this checkup is 7 days. 7 days, you are not able to capture all the tankers coming up and down. So you just imagine about all the constraint within that area. So in some cases, we go to a subsea, like we discussed before. We have the subsea wells, and then pump straight to the FPSO. The processing plant will be here, and then they will do the storage, and the shuttle tanker will come in every week or every 5 days, just to load. Depends on how big is the production compared to the storage capability. Okay. Some other campaign like this is near shore, because if you have a field which is this is the ocean, this is the near shore. So sometimes you have a field here, you can have some of the field here. This is in Australia. What happened? They have a small platform where they can tie in wells coming in from the other area. They go in here, and then sometimes you have all the subsea wells that can be linked to that, and then going straight away. So without processing. So some of the field here, the processing is done as on shore. So all the oil will go straight away. Yeah? So that this platform is actually, I believe, going to be drilling a well. There may be about 10 wells here. So they do not need the processing platform because they can pump straight away the crude to shore, and then processing will be done here. Just imagine it's much cheaper because when you have the processing facilities onshore, it's cheaper than offshore. So this is a marginal field where they can, and then it's near shore, and they give the advantage for them to really avoid the processing platform on offshore, So they transfer that to the onshore side. So this is how the strategy will come in based on the economics, based on the option, ideas, thinking outside the box, whatever lah. Okay. Typical development plan, you can see that, for example, mostly in Sabah, this is in Miri, in Sarawak. You see that you have multiple drilling platform. You have, for example, this is 8 wells, and then they have about 6 wells or maybe 10 wells here. All these wells will be producing and going straight away to the pipeline, from well to the pipeline, going to the processing platform, everything there. So if this platform produce 20,000 barrel, to 2020 is about 60,000 barrels. So this platform will be able to process 60,000 barrels. But of course, not thinking about maybe some misjudgment, some better results. Maybe from 60,000, it can go to 80,000, for example, for the first 5 years. So the design of this platform can handle that kind of range. For example, if the requirement is 60,000, but they will put in 80,000 barrel capacity to process, just in case that somebody else will tie in, or the result is much better than expected, so they have more production. And of course, the sizing of the PSO will depend on what is the production rate. So the production rate is 60,000, so time by 10 is 600,000, at least minimum 600,000 capacity based on the 10 days, storage time or transit time. Okay, that's typical development. We have multiple drilling platform or drilling wellhead platform, and then we have subsurface platform, and then it will be linked to the storage, where it's just for storage. If because the facilities is there. If, for example, in some area you have only one wellhead, and then you have a small platform, and then you try not to have the facilities, too much facility, only about 30-40% function, and then the rest will be done by the floating storage. So if floating storage becomes FPSO, floating production, storage and offloading. So it's depend on strategy. Okay. It's a typical example of sharing. For example, you have these multiple wells in Sabah and Sarawak. This is actually in Bintulu. This is all the gas coming in from this is for gas, for Bintulu gas. And then I think the Miri side is going to be all the Miri oil terminal and MCOT. We have all the field here. We go to the facilities for storage and processing. And then you can see that some of the area here, because if it belong to one company, like this block, it belong to Shell. So Shell we have their own right to link among the platform. So once you have another platform, let's say you have another operator far away, so you can see that now you have to share, because this block belongs to company A, this block belongs to company B, but company A say that if I want to produce independently, I'm going to spend a long distance of my pipeline going to offshore. So it's going to be very expensive. So they will ask for this another company to join in. So they will try to produce this field, link to their to the neighbor, and then they have to pay the tariff of using the facilities, and then it's going to be transferred to shore. So that's how the coordination of sharing, to help the company to have the economics. Because if without sharing, then this project might not be economics. So, because of the size, the distance of the pipeline from here to here is about, let's say, 500 kilometers. So you're going to be exposed yourself to so many uncertainty, and then the cost will be very high as well. Okay. So drilling strategy. So for drilling strategy, of course, once we have that, you must understand drilling contribute about 30 to 50% of the project cost. So that's why the drilling itself becomes so important, that you must have the right strategy, the right approach of drilling to be able to reduce the well cost. because the contribution of well cost to the project is 30% to 50%. For big field, of course, it's going to about 30 to 40, but for small field, it's almost like 50%. It's more on the well, because the well itself is special. We drill a well with all the technology, with all the expensive services, with its special rig. Then, of course, one well, normally we go through sometimes like 20 million to 30 million per well. So it's going to, and then we have 100 wells, it's going to be about how much? Yeah, it's going to be about under 200 million, something like that. So FDP is developed through a multiple discipline, as we discussed before. We have geologists, geophysics, and petrophysics. I think the function here, you can explore through Google or from our chat GPT, to understand the function of each one. Okay. And then this is example of multiple well. So in this well, you can see that they have so much well. I think about 24 wells, 24 slots. So there are 2, 4, 6, 8, 10, about 20 wells altogether. And each well is going to their own target. So you're going to the reservoir, and you just imagine that we have to manage the production from this well. For drilling, we want to, because offshore, we want to have one drilling center that can manage 20 wells, going to each target. So if the reservoir is shallow, that means that you're going to have high angle to each reservoir. So it might be difficult. We have to think about drilling with a high angle well, have another complexity, another difficulties. So there'll be some cost additional there. But if you have a deeper reservoir, then your inclination, the additional will be much less than, let's say, 50 degrees. Then it's much more convenient to drill. And then, of course, the drilling will be faster, less problematic, and so on. So drilling impose another criteria where the formation reaction, the formation quality, the pressure itself will dictate how much the well cost will be. For high pressure, high temperature wells, you're going to talk about 50 million per well. Normal well, oil well is about 20 million or less. So it's just so much variation in terms of cost based on the well condition, the challenges in when we're drilling the well, the directional. Okay. This is the place to visualize the 3D of the part of the well. So you have all the reservoir here, and it will be touched by all this. So what happened? All this high angle well is the well that been drilled later on. For example, after the well been produced for about 10 years, then we understand the reservoir. We see that there's some potential reservoir here, some here, and some over here. Then we decide, okay, we drill more wells on the platform. So the platform might have a slot of, let's say, 24, but knowing that you might have potential in the future, so rather than doing the 24 slot for well, you might increase to 32, for example. So that kind of situation. So this is two drilling center. This is platform A, drill maybe about 20 wells, and this is platform B, drill another 20 wells. You can see the angle, how the profile is going to be like a 3D. You're going to be built, you can build the angle, hold the angle, and drop the angle and hit the target. Some really is very short. Some is a call it pregnant lady. So they build up, and then they curve, and then they hit the well, just because they want to avoid the collision from one well to another. So every time you drill, for example, you drill 10 wells, the 11 well we go through all the webs itself. So you have to be some collision issue. You have to really make sure that when they drill, you're going to go through certain safe distance and manage to get to target without hitting another well. So it's all quite complex of drilling. You can see the complication, the strategy, what is the solution, and so on. Okay. So I think like for the directional well, you can see that some of the well can be drilled, horizontal. Some is 3D well, that you can see we call it pregnant lady. It all can be all the 3D wells. And then some well they can have multiple wells, a stack material. This is the multilateral wells. This is also multilateral wells. But in Malaysia, we don't have that characteristics of reservoir that can allow us to do this is multilateral. We have one project in Sabah, in Miri, where we try to implement the first multilateral, but the problem is that all the junction here fail for sealing, so we had difficulties to really manage the production. So we don't see in Malaysia that the technology is always be quite new for us, but not some other area. Some other area they have been matured, they have been successful in multilateral, and we have difficulties for this kind of multilateral. when I was in Saudi Arabia, Saudi Aramco, this is the criteria of multilateral that I have. We go to the same reservoir, so we drill one main bore to the target, and then I pull out, and then I try to subtract, going to one side, and then going pull out, and then subtract to another side, plug the hole, change new bit, and I try to drill this subtract here, this subtract. So which one is about 500 to 300 to 500 meter. And this well length here is about 5 to 6 kilometer. So we have the length of 500 meter additional. So this is called the multilateral, they call it multi-exposure reservoir concept, So this well, when I was there, we are able to produce up to 50,000 barrel. It's a lot. Then we run about, this is 7-inch casing, and then produce about 50,000 barrel per day for one well. Huge production. So this is more or less some understanding about if you're onshore, they can use drill vertical well and then can directional well to hit the target. Because you have multiple target, you have to hit the sand here. So that's why you can drill vertical, you have to directional so that you touch all the reservoir because they are on the different layer, different location. If it's so deep, for example, like shale gas, you can drill and then you drill horizontal well across the sand so that you fracture the shale and then you produce the gas or oil. In some area, you have somewhere like coal bed methane, because it is somewhere in I think Petronas, we have some share in Australia in person going to the coal bed methane done by the local agent lah. We put a share there, and then the methane here we produce. They drill so many wells across the zone and produce the methane. It's shallow. They can drill very fast, and they're using the coil tubing rig with hybrid rig. They can drill very fast. So when I talked to one engineer, he mentioned that one well can take about 5 days. So 100 wells can drill about 500 days. And so they have divided by 3 wells, 3 rigs. They can do it in 1 year, 100 wells to plug in for the coal bed methane.
But they have a question in the chat box, but answer.
Okay. Now let's go to chat box and see, okay, follow. So that's something to do with the calculation and so on. Very interesting in terms of strategy, variation, how to manage challenges. Okay. So let's go to the chat board and start to see the question. Okay. I wonder whether the drill can be steered. Of course, the technology nowadays, we always go for the steering. So we call it RSS tool. It's a rotary steerable system where we can steer even by rotation. It's a technology that helps us to reduce tripping for correction run, reduce for us to have error, difficulties to steer. Because what happened with the steerable system, we managed to do the correction almost immediately. And then with RSS system, we able to rotate the string. A rotation of string means that a better hole cleaning. So the revolution of technology using RIS, rotary steerable system, helps a lot in drilling to reduce the time, avoid all the drilling problems, and we managed to hit the target within the shorter time. Even now, I think like ourselves, Azmia, we are also having the service provision to do fully automated drilling. For example, you set a target, and then the computer system will more or less direct those RSS to drill to the target without any human intervention. It's just computer, you're setting up the target, it will adjust itself based on the current profile and try to follow the profile and hit the target in the automation mode. So that is coming in lah. But I think we are supporting the services. Hopefully more people will try to engage us to do this automated drilling to target. Okay. So once we have that, of course, well construction will come in. Interesting well construction, because when we do construct a well, it's another skill. So for me, Cik Razak, myself, we are drilling engineers background. So this is the area where we get involved, getting data, analyze data, go with the option of drilling, what kind of drilling system we should use, how to really shorten up the time. Because the shorter the well time, the lower the well cost. So in our offshore operation, time is money. So the moment we can reduce time, that's it. So in our computation, our judgment, if the technology is expensive, but I can still reduce the time. So for example, the rig rate is $100,000 per day, and the total operating cost, so including the helicopter, the supply vessel, the fuel, the third party, could be around $300,000 per day. So rig cost 100,000 plus 200,000 services and logistic is $300,000 per day. So we can say one day we can hire a tool that we pay for 300,000. This is the comparison. So we always you consider high technology in our offshore drilling because this is cost and our operating cost is high. So the moment you can say one day, actually it can pay off, whether it's your system, your mud system, and so on. Okay, interesting. So now we go more or less on the last project, and this is the last topic of project economics. So project economics is something that normally the engineer we don't get involved. But for us, since we are involved with the project, we are mostly the leader of all the project that we have to know a little bit about project and economics. Then of course they will help us to understand strategies change, cost change, and then how we manage the uncertainty and so on. So for upstream industry, the high risk in all respects. For the economics, it will involve a lot of high risk, high expenditure, billions. For example, we're talking about a project like a gas field, Kasawari from Petronas, is I think they are approaching about 2 billion US dollar. And we have, let's say, Murphy, when they do the deep water, they are talking about almost like 1.5 to 2 billion US dollar for the project. And for the small field, like some field that we talking about, for example, in my case, for Talisman, we have the knots, the what call it, the Bunga Catwall and so on. The range of expenditure about 500,000 US dollar, and we are producing close to about 40,000 barrel per day. So it's very good project. And some of the area, marginal field, we can see that some marginal field, they are only producing around a range of 3,000 barrel per day. And then the cost economy is about, they go about 150 million to 200 million for the total project. So it depends on how, where are you? If you are close to the shore, then the economics is much better. If you're too far offshore, then you have to think about, you must have big reserve to be able to make it economics. So uncertainty will be a lot, like reserve amount. Reserve can be up and down. For example, the reservoir people, the geologists predict that it's going to be 200 million barrels down there. Recovery factor 50%, so it could be 100,000 barrel, 100 million barrel recoverable. Then of course, you're talking about how many wells. Maybe the recovery factor is less because you're putting less well, and then the production rate might be low because no, the commercial damage is worse, and then so on. And the cost of oil price will be also up and down. So your profit margin will also depend on oil and gas, So it's a lot of uncertainty, but as I mentioned to you, we have the engineers, we want to be professional. What we do, we don't want to over-promise. So we don't want to say that, oh, no, you can have such a huge profit. No. We always say that this is the most likely case. In our mind, in our heart, we believe that is much better, but we don't want to commit because we know that so many uncertainty. So we always go to something reasonable, something conservative. So when we implement the project, when more data come in, then we start to come in with a better estimate and prediction. Okay. So for example, the effect of recovery factor on the well. For example, we have recovery. For example, we have the oil in place 300 million barrel. And of course, for same thing, 300,000 barrel, 300 million barrel, and the recovery factor 35%. So we can only produce 100 barrel, 105 million barrel for the field. And this field, if recovery factor about 30%, is going to be 60 million barrels. So it depends on recovery. So we run economics. For example, this reserve here, 60 million, will last about 14 years, about 4,600 years, or about, that is for the days to produce the amount, average. So we have the average production 12,000 based on this number of days. Then we calculate economics, for example, to produce the 105 barrels. And of course, the project capex is 1 billion. OPEX is also 1 billion. And then we have about the profit, about 4 billion profit in 35 years. So 4 billion profit in 45 years after we know the revenue is 6.3 billion minus your capex and your OPEX. That means your profit is 4.25 million. So divided by 25 years, we have the average of 207% profit based on your project cost. So for example, your project cost is 2 billion. So you're about 200,000% profit over 25 years. So you divide 25 is about 8% only, not much lah, but still this is the number. But you compare to the lower recovery factor, 60 million, you're going to produce a shorter time because of less volume. And of course, you're going to spend about half because I think for example, we're talking about revenue is going to be almost half because of less production. And project cost will be less, OPEX cost will be less big. So you're going to have profit, revenue minus your CAPEX minus your OPEX, then you have your profit. For 14 years, we have about 200%. So you can see that more or less they are about the same, in terms of but in terms of the volume, the 2.4 billion profit versus 4.2 billion profit is actually something different. But you talk about the years, it come up more or less about the same profit margin lah. So just to show you that the current factor might have impact or might not have some impact because you're talking about you're organizing a different concept of development to make it cheaper, and then you are going to have more or less the same profit. So managing the CAPEX and OPEX. Okay. Okay. Let's see the chat box. Thank you. I think that's good. We want to see more question. Okay, is it going to be the first question like we assume? Let me see. Okay, the first question, is there anyone or specific unique role that drives the drill? Means someone drive that drill remotely, we assume so. I think we have done that, we have covered the information. The next question, is there any real worst case where the economy do not give a good return after the work and investment have been done? And what is the normal practice to solve the shortcoming? Okay. Normally, like I mentioned to you, when we do the economic analysis, even the field development plan, we have put in all the risks involved. And sometimes if there's a failure to identify the proper risk or we underestimate certain risks, then it come up to a situation where your delivery or your revenue is much less compared to your investment. So when your revenue is less than your investment, normally there will be about the process of cost cutting. For example, some platform might be having a big facilities, whether we have to downsize the facilities, and then we reduce the manpower when we try to negotiate, based on certain requirement of, like, for example, the tariff. So we will talk to our government, because at that time we have, for example, the profit sharing is 80-20, 80% to the government, 20% to us. Due to the economic constraint, we negotiate with the host government, they negotiate on the profit margin, then they come back to the more or less the we call it the profitable area lah. So it's a win-win situation. So for win-win situation, it always be room for discussion. Okay.
Patip, just wanted to add a little bit
Yeah.
I think Fahmi raised a really great topic to discuss further lah. This is a real issue, and one thing that everyone need to understand is that the monitoring of cost is for the project. Doesn't matter whether it's just drilling, ataupun the overall project implementation is done on a daily basis, because we kind of like know what basically is coming in, and then we project every single day. We project and see whether we actually are going to overrun or underrun. We basically will discuss ahead of time. So it's not going to be like a surprise. Oh, we are losing. So whatever that Patit was mentioning just now, renegotiation of the terms and things like that is done before the project is actually completed. So on the daily basis, we monitor costs. Yeah. All right. Thank you.
Okay. So that's more or less the understanding. Something the question can also be presented in such a way that, for example, Fahmi mentioned that if we going with the project based on our initial estimate, and then actually the prediction is wrong, for example, then we are in the middle of production of 5 years, for example, and then we find out that you are not going to meet the profit margin. like I mentioned, and then of course you have room to more or less present your case to the government, and then of course the sharing will be more or less negotiated. This is example of the PSC 1985, just to give a good understanding about how the share of the profit. So we have the gross revenue, the production, we sell the oil, so we have the revenue. So let's say for 1 year, we have the revenue of certain million. So the royalty will be taken out of 10%. So 10% royalty will be taken out straight away from the income. So the 5% will go to the government and 5% go to the state. But since in our government always say that the area is belong to the federal, not to the state. So they have all the 10% to the government. So for Sabah for Miri, since they are very close to the shore, they have also claimed for the 5%. So that's why Miri they can have the 5% royalty and another 5% going to the government. So just imagine you have the profit straight away. They pull out those value for the royalty. And then once you have the minus your 10%, you have the 90% of the revenue. You're going to go for cutting for the project, for shielding to 50% for oil company to claim. For example, if you are the operator, we spend about 200 million for the project or 300 million. So we're going to start asking government to pay back. So they pay back from the production revenue. Because Petronas or the government, they are not give you money straight away. They say that, okay, I only return back your investment during production. So this is mostly the strategy lah. So shilling for cost that you claim from your revenue is 50% for oil, for example, for oil, and then 60% for gas. And that's how much you can claim. 40% is part of your sharing of investment lah. I think this is also another area where you have marginal field. We can talk about some adjustment of this number to get more return from the government. So it's another area for discussion before we sign the contract, PSC. So we once heard that, of course, we're going to compare with the actual project cost. Normally, project cost, we say 200 million, we start to drain the revenue for 5 years or 10 years. Normally, some good field, I think the government will start to contribute to the project cost between 5 to 6, 7 years. And then after that, the government will have the full profit margin lah. After we take out all the project costs, paid off the project costs by our own self. So when you have the project cost, you have this after you minus all the project costs, we have the balance, or this is called profit. Profit all. After you minus revenue, you minus actual project, and this zero profit we distributed by sharing. So some of the previous PSC, they talk about if the first 10,000 barrel per day, 50% we go to contractor, 50% go to Petronas. If you have a higher next 10,000 barrel, you have a better revenue, then contractor we have only 40%. So in other words, Petronas or the government will ask for more share when it's more profit. See, sometimes you are more or less you are almost having the same profit lah, Like the higher the production, we get less, but in terms of the monthly, the yearly, you have to have that profit almost like constant lah. But Petronas we get higher and higher as we produce more and more, or the reservoir is bigger and bigger lah. So that's more or less the understanding. So based on the average calculation, profit for Petronas will take about 38%. And of course, this is based on petroleum income tax. So the rest will be ours, maybe on the contractor side lah. So contractor cash flow will be here, about 38%. After we minus tax, 38%. Still not bad. The profit all here, after we deduct all the project costs, and then with 38% to Petronas, and then 38% to contractor. Okay. I think we go through the comparison. This is another interesting topic to see how the PSC changes. In 1976, you can see that Petronas is talking about the percentage, 28%, and then of course our partner about 10%. So I think later on we see that when we take over, ExxonMobil enjoy this and enjoy this percentage. After some time, we see that it's too much, and they are getting too more. So we revise the PSC, and then we start to really reduce the percentage from the partners lah, because we realize the government needs more. This is on the royalty side, royalty plus so it's going to be more or less by the government, but government want to ask more. And partner, the operator will get better because we want to encourage people to come in. So you can see that the 1985 PSC and so on, we start to offer better option for the operator, and of course we get more people coming in with this strategy. Deep water, you can see that is normally is going to be quite small because the risk is high. Even the government willing to to reduce the share, knowing that the cost for the project is high. So the cost of the project is going to, we are willing to sponsor the cost. The government is willing to sponsor the cost at a higher percentage because of the water. Otherwise, nobody will come in. So we say encourage people to come in with a better offer. And of course, for the risk contract, of course, we try to improve the calculation. So we say that to government, we can reduce, Petronas can reduce the share by giving more to the government. But same cost for this contract lah. But the contractor get more. Okay. Cash flow tabulation, you can see that to have the flow and the calculation of economics, what you need to have the production profile.
Comment dalam chat box, guys.
Okay. See, so like Petronas have to share or hand over certain oil and gas asset to Petros. This may affect the Petronas and cause some cut losses. So actually, there's some misunderstanding about the Petros and Petronas. So what happened actually when we talk about the development field, normally the development field will be done by Petronas, and then Petros will start to do the distribution. So Petros we start handling the onshore business activity. For example, we produce gas coming up to shore. Shore will start to be processed by Petronas facilities, but selling will be handled by Petros. Same like oil. Oil be coming up from offshore, going to the crude terminal, and then once we process from crude terminal, marketing will be done by Petros. So the advantage always the Petros we have the share of the business having the sharing or the selling market. For example, they have the commitment or they have the agreement from Petronas to sell the oil at 60 barrel per $60 per barrel, but they managed to sell at $65 per barrel. That means they have the profit of 5 barrel. So they only looking for the distribution or aggregator for oil and gas. So not the project itself. So Petronas normally when we do the project calculation, the operator will only concentrate on producing the hydrocarbon to shore, and after that Petronas will handle. So like in this case, Petronas will lose a bit because the margin of marketing is lost, but in terms of the value of the profit overall of the we call it profit oil coming up from offshore is still handled by Petronas. So the impact is not that significant, but still there's something lah. But of course, I think we have yet to see how they manage, because sometimes if they fix the price of offshore, for example, like 50 barrels per barrel, $50 per barrel, and they can set 70 barrel, of course, it's very unfair. So I think there's a lot of discussion about can Petronas share that the distribution cost as well. That's that kind of situation. Hopefully, I answered that. Okay, for me, interesting, Petros. Okay, so to have the economics, first of all, you must have the production profile. So there will be the help of the reservoir engineer. They will tell you what's going to be the profile. Like the first year, they can produce 8,000 barrel. Then since more oil coming in, they start to have 16,000 barrel consistently up to maybe about 12 years. And then the production down to the economics. So if for example, if the PSC is 20 years, we start to shut down here. There's still more oil, but we're going to hand it over to the host government, Okay. And then, of course, once we have this profile, that is where you can start to see the oil pricing based on what is the price you want to use in your economics. So, for example, in the World Bank oil prices, we see that it's fluctuating from 2000 to 2023. So we have to predict what's going to be the next for our campaign. For example, our field will be coming from 2035 to 2050, 35 years. So uncertainty will be there. It can be going up, it can be going down. So the judgment will be that, for example, in this economics, we confirm that it's going to be at $60. We declare agreed by the government, by the our management, then we use $60. Currently, it's about 70 plus. The oil price is about 70 plus now. And normally, we have seen oil price about 100, which is within this year. And then, of course, we've seen that it's all within that $60 lah. Because as per the calculation, discussion, even in for Saudi Aramco, they foresee that $60 is a good start to really stop the shale gas, because shale gas and shale oil in Canada, they can survive if the oil price is more than $60. So that's a strategy business. If it's less $60, all the shale oil and shale gas will die, So that's a strategy business competition lah, we call it. So it's all based on the market value, but we use about 60. Some company willing to use about 70. So it based on sometimes Petronas we always reject lah. If you propose $70, $80 barrel, they say no, it's too aggressive or too promising lah. So sometimes they ask for $50 or $60 based on the confidence. Okay. It's some table in calculation for economics. You put a number here, $50, and your OPEX is like, for example, $5. Inflation rate $3. So you're going to consider for a year after 15 years, for example. Then how much we have the production, 9 million, about 10 million barrel. Your NPV 0, 10, 15 will be evaluated. And then you see the result. So the profit, based on the profit margin monthly, how much you're going to have per million, 600,000, 5,000, and 4 months. So this is more or less some example of cash flow. You have to use what is your inflation rate, what is the oil price, what is the barrel. So you can see all this number is adjustable. So when you run your economics, you start to have certain basis. If let's say inflation rate 5%, what is going to happen? Oil price $50, what is going to happen to your economics? All is adjustable because we can do it in some. Nowadays they have this simulation, economic simulation that can be run. But for me, I've been using mostly the Excel sheet and try to really play around with all the numbers here and get the results of NPV. So for example, this is NV10. NV10, this number here, you can see that monthly profit is about, I think the total is about 560 million for 15 years. So if you have the share of 2080, then we're talking about 560,000 dollars per month as our income. So is it okay or not? So it's based on our company, our shareholders to agree on the potential income for the project. Okay, so economic as well on the table. You put in the table by year this way. What you have down here is a simple version of going another way around. But if you go a bit detailed, then you can put in what is going to be the price for each year, and then what is going to be the production for each year, and then you can go even detail. You can put every variation of prices you like. Excuse me. Okay, so it's all the capex cost, the OPEX cost. You come up with all the numbers in your spreadsheet. Okay. So commercial analysis, you need to mention about what is the NPV, net present value at 10%. So what is meant by an NPV 10%? NPV 10%, let's say 20 million in your number, indicates the project give additional value of 20 million compared to investment in a bank, which gives 10% rate. So if we call NPV 10, that means that you go to the bank, you have the 10% interest rate, that's what your income will be. But if in our case, NPV number here is really beyond that, it's getting more than your interest rate. So if you have zero, NPV zero, that means you're still good. Why? Because you still have the normal interest rate. If you go to invest, you get to keep your money in a bank, you get 10%. So NPV zero is that it's just like you're going to have a bank rate of 10%. If you use 20%, it's 30%, different. So IRR is the investment rate of return. It's a number. If you set 14% as your company set 14% as your guide, but it's meant that the project will give IRR lower than 40% is not going to be considered economical. It might be return might be 50%. Some company they set 20% as their target. So we have to really run the economics. Make sure once we have more than 20%, then the project will be presented for approval. And so on. Okay, let's go to the chat box. Okay, then we have, like Petronas have to share. Okay, what is your opinion on the decision making 50-50 joint venture like Perfect Chem? If Petronas Aramco tak setuju on something, how they decide? But So this is actually outside the FDP plan, but it's more on the investment. It's normal. We call it normal business engagement. So for example, in Pengerang, so Petronas and Aramco had a 50-50. So what happened actually, for example, Petronas have presented the case that this project involve high risk. So Petronas need to diversify the risk, share the risk with other partner. So they invite partner, and then it seems like Aramco interested because Aramco see the opportunity. Maybe when Aramco see our presentation, they see the opportunity that even though there's high risk, but still there's a lot of potential to expand. But what happened actually when we go through, what happened? Aramco tried to disagree purely because they foresee that most of the profit, for example, is coming from the oil that they're coming from Saudi Arabia, for example, or they are going to arrange most of these businesses for the penerang. So based on their contribution, more contribution to the business, they're asking for more profit. Of course, for us, yes, you done your job as a partner, we should be able to help each other. But for me, what happened is always going back to win-win situation, justify your reason, and then find out, and then come up with a conclusion that what you should do. For me, it's always be a decision because nobody will try to back off. So nobody will try to put a formula. For example, if we have a certain situation like certain profit, then the ratio will be different. If we think that, for example, this is the volume, we have to monitor the volume coming from mostly from Aramco side, then the ratio will be different as well. Either it will be premium change, premium paid, and so on. So all those kind of formula can be set up so that we come out the win-win situation. Okay, Shafiq, eh? Yeah. Yeah, we continue.
Okay, let's take it back. Okay, hello participants. Since it's already 12, I understand that we should have finished the session. However, we still have a few more slides. In case you guys can stay for the
5 minutes.
if you can stay for till the rest of the session, you can. But if you need to leave, you also can do so. Just know that we will be uploading the session to YouTube, so you can just revisit the session until the end on our YouTube channel. Okay, thank you.
Okay, yeah. Okay, I think we're almost to the end. So this is more like the commercial analysis, just to give you some idea that when we do the economic analysis, we cover all the inflation rate, royalty, and so on. And of course, the result will be what is the PIR, IRR, and this is the MCO is maximum expenditure, the exposure. So the project, for example, what MSO mean is that maximum capital, the project will require 903 million. So the operator have to stand by this amount of money, and of course when it start to produce, all the income will be more or less paid off, and then your investment will be getting less and less lah. So NPV, how much your NPV or the sensitivity will be done. So this is more or less the summary to present to management so they can easily understand the pattern and so on. Okay, sensitive analysis, we try to see what will happen. So in our sensitive analysis, you can see that we try to see what happened if the cost overrun of OPEX and so on, if the delay in schedule, what is going to be the loss, or price up and down, what will happen, So this is the last slide I've shown you. So this is based on the firm number that we have, the best information we have the NPV of 13 million. I said 13 billion, I think 13 billion for this one. Okay. So this is 30 million. 30 million is an NPV based on normal assumption that we already put in. What if the field cost, the OPEX cost, the CAPEX cost increase by 20%? Then we have, this is less. We have the project cost is less by 20%. We have the NPV increasing to 40 million. But if the cost is less than is more by 30%, we're going to have NPV less, 13 million. This one case. The second case, what production? If the production drop by 20%, our NPV will be less. So it's negative. So we're going to have less income. So the impact is going to be huge as well, because from 13 to 10. But if the production is more, then we have 15 million. So we have additional revenue from that. So then we go to what is happened to this is the production now is oil price. If the oil price drop to 40%, then we have to have only 8.2 as our North cash flow, is our NPV. This is a net cash flow that we have at the end of the project is 8 million only. But if we have the price going up, oil price going up, they have to have about 90 million. So based on this, we look at all the worst number NCV. So it is possible that you're going to be impacted much on this, on the oil price. So we know that at the oil price, if we 40%, we still survive or not. If we still survive, then it's going to be a good economics. We present to management, we say that based on our assumption, we can manage uncertainty based on the possible price down by 40%, production down by 30%, and the capex cost of the project is down by 20%, we still have a healthy economics for the project. So we get the approval, then we proceed with the execution of the FDP. Okay, I think thank you very much for the attention. So if you have any question, I think CBC have a chat box, for you to come in and then try to even send us email for your question. Then we try to answer as much as possible. Thank you, everyone, and Assalamualaikum.
Waalaikumsalam. Thank you, Patip, and thank you everyone for being with us this morning. Okay, this will be our final session for the NTW 2025. So thank you, Pak Latif, for delivering this session. We hope this session has given you a clear overview of key elements in formulating a comprehensive FDP, from setting up a competent team, conducting D&D assessment, defining development strategies, understanding project economics and the fee. Okay, it's a vital part of upstream planning, and we hope it sparked your meaningful insights for all of you. I also would like to take this moment to sincerely thank you everyone for your relentless support throughout the week. We have a pleasure to meeting many of you. We have also recurring participants. As we know, we have Fahmi and everyone else that have been asking questions for a more participation, for two-way communication. It was very interesting. So basically, a quick recap of our NTW session this week. We have Monday, understanding drilling business, introduction to upstream oil and gas. Tuesday, we have automation in drilling operation and drilling fluids technology. Wednesday, we have well cost estimates. Thursday, we had origin of hydrocarbon and principle of well integrity. And lastly, we have today field development plan, and all this session, we have a recording of it, and I'm currently editing all the videos. So I've been uploading the session to our YouTube channel. You can just check out YouTube Fazmia Technology for all the videos.